The math works perfectly. But what does it mean? Quantum mechanics is the most accurate theory in the history of science. It predicts the behavior of particles with stunning precision. But when it comes to what it's telling us about reality, physicists and philosophers still argue. At the heart of quantum theory, the probability wave function. That encodes all possible states of a system. But what is the real meaning of it? A physical wave? A mathematical tool for calculating probabilities of all possible outcomes? Or something else entirely? In classical physics, systems have definite properties. A planet has a position, momentum, trajectory. In quantum physics, an electron has probability amplitudes, but only until the measurement has been done. Before the measurement, the electron is in a superposition, not here or there, but in both places at once. And when any particle property has been measured, it snaps into a single outcome. This phenomenon is called quantum wave function collapse. But collapse isn't part of the math. It's an added postulate and does not have any mathematical ground. This is called a measurement problem. The most widely taught view on this contradiction is the Copenhagen Interpretation. It says the wave function is not a real physical thing, just a tool for predicting measurement outcomes. The act of observation collapses the quantum wave function. As a result, reality becomes definite with only one outcome. But this raises deep questions. What counts as a measurement? What role does the observer play? Is consciousness required, or just solely the interaction with the environment? Einstein objected. He believed in an objective reality, one that exists whether or not anyone is looking. He famously asked, "Does the moon exist only when I look at it?" In response to this problem, Hugh Everett proposed a radical solution: the many worlds interpretation. No collapse, no special observer. Instead, the wave function evolves smoothly. When you make a measurement, the universe branches. In one branch, the electron is here. In another, it's there. All outcomes occur, but in different worlds. This view treats the quantum wave function as a real entity, and it removes the mystery of collapse without changing its mathematical formalism. But it comes at a cost. An infinite number of parallel universes occurs every moment. Many worlds is elegant mathematically. But does it really describe the world we live in? That depends on how you define real, and whether we are able to check the validity of this idea. Then there's a newer, more speculative idea, the simulation hypothesis. What if quantum uncertainty isn't fundamental? What if it's a computational shortcut? In this view, the world isn't continuous, it's digital. Reality is rendered on the fly. Particles don't exist until they need to be interacted with, like a video game loading only what the player sees or feels. This might explain why quantum systems behave randomly, and uncertainty is a necessity of the theory. It may explain why the universe runs on clean, elegant math, just like code. The simulation hypothesis isn't mainstream physics, but it reflects a deeper truth. Quantum mechanics forces us to ask what's real, and whether reality is as solid as it seems. So what does it all mean? The math works. It predicts outcomes. It powers lasers, semiconductors, MRI machines, quantum computers, but its interpretation, Copenhagen, many worlds, simulation, remains unsettled and incomplete. Perhaps one day we'll uncover the reality behind quantum theory and grasp what it reveals about the fabric of the universe and the true nature of our world.